Okay, so this was the experiment that I had requested people to try from their homes, and a few of them have responded. So I'll just go over the photographs that they have sent. Ashwath and I tried it out also in the physics lab, and I also have some pictures of that. Now, reality is always stranger than what idealized circumstances can produce. So as people try to do this, you will find out that finding a shallow bowl is a problem. Finding a small enough piece of mirror that can fit into it could be a problem. What kind of light source should you get? That could be a problem. So it's really to kind of work through those kinds of issues and see what actually happens. Um, is the essence of trying things out for yourself. Things are not ideal, so if they are not ideal, then you do something about it. So Hardik sent this series of pictures, and he said he tried out a variation of it. So he got a what looks like a kind of borosilicate glass bowl that's used for casserole, baking dish and things like that. So filled up water in it, shined the light through a mobile phone flash, and kind of, I think, just kept it off the edge. Did you, Hardik, if you're here?
Yeah,
Was it seems to be just off the edge. So that's what will
yeah,
produce this kind of an elongated picture over here. And as you can see, it's in the fringes. Yeah, it's in the fringes that you can start seeing the reds. So there's a slight amount of red, and perhaps in the next picture you can see it a little bit more closer. So the at this point over here, you can see that there is some yellow, there's some green, a little bit of orange, right? So you see it along the fringes, and you see this specifically occurs between the light areas and the dark areas. Yeah. So this was one of the dominant ideas prior to Newton's work, that light was actually created because of an admixture of darkness and white light. And this idea was so fixed in the minds of scientists of the day, the natural philosophers of the day, that when Newton proposed his ideas about the source of colors as coming from white light splitting into different parts, and despite all the difference, so it was not just one experiment with prisms. He performed a series of experiments, which is again given in that book Tarasov and Tarasova, written in fairly plain English. I read them through yesterday and today morning, and gives a very good account of all the different misconceptions that he sought to clear out for himself first. And despite all the evidence that he gave, there were people who still wouldn't believe, and primarily because they also kind of asked questions which Newton himself could not answer based on his theory of colors, which was that they asked, why is the sky blue, say, for example. And this was actually a very famous German poet called Goethe, who was, apart from being a poet, who was poet philosopher, he was also very interested in light and colors. He had written a small treatise, a booklet of his own on light and so on. So when he came to know about Newton's work, he reacted quite strongly to the idea, and he sort of said that why is it that Newton's theory of light does not explain the blue color of the sky, or that at early in the morning, when you see the sky just before sunrise, you see a blue hue in the horizon, and you can easily see that there is brightness below and darkness above, and that the blue is an admixture of these 2. Or for that matter, during sunrise, during sunset, the sky appears red, and that is because of. So actually, Newton at that point of time did not have answers to these questions, and we will in fact a little later, the last section of the chapter on light, we will study the phenomena that actually finally explain this, and that had to do with scattering of light. And because some of these questions could not be answered directly from Newton's theory of color at that point of time, people did not accept his theory entirely. So moving on now, so this is another picture from a different angle. Also see the fringes over here. You can see that there is a color at the fringe over there. Here again there is a bright spot, and then there is a fringe with reds, and it's again not very clear why these this kind of pattern appears over here. It will be worth having a look at the container and the structure of the container to see why is it that these patterns appear over here. And then moving on to Patanjali. So Pattu sent this quite nice one. I had asked him if he could share the setup, in the sense that how did he actually make this to happen. Here you can quite clearly see on the white screen that there is a blue and purplish section over here, and this is moving into lighter and lighter colors, turning into green, yellow, and then you see some hues of red appearing, and so on. So this is quite well done. The picture is a bit grainy, I suppose, because you have done it in a dark room, and it's in a dark room that you get the best contrast to the different colors. So if there is a lot of ambient light, you will not get that kind of a contrast. So yeah, this is again from Pattu, showing it on the wall, and again you can see the change in colors from blue going all the way up to red. Another picture of the same thing. I think this is also Pattu, yeah, and you can see the fringe over here, the blues and so on. Nicely done. So this is the setup that I tried. We had a table lamp which had a normal halogen, sorry, not a halogen, an incandescent bulb. And the incandescent bulb I focused on a tray with a mirror which is partially submerged. This is the kind of mirror that you would have used last year to perform experiments on light. And then naturally the light that is reflecting on the surface falls on the wall or the background behind over here, and this is what I saw. So you can see some ranges of colors. So there's the blue over here, again there's the purple and blue over here, turning into greens and oranges at the fringes over here, and this was of course using a prism, and this was done at the Gundalwadi school, one of the last few times that we visited the school over there. So using a prism, training reflecting sunlight from a mirror onto the wall, and then using a prism placed on the wall to do this dispersion. So here you can see the dispersion pattern quite clearly. But see that the color is inverted over here. Okay? In most of the cases that we saw, the blues were at the bottom, the yellows and reds were at the top, whereas over here it's slightly different. See, here the blue is at the bottom and the reds are at the top, but here it's the other way around. So wonder what created that. And then the last image that I want to show you is this pattern that occurs over here. I wanted to see, and this is because mostly I read what Newton had done, and what he had done is he had used a biconvex lens, that is a converging lens, and showed it on the path of the converging, of the spectrum. and he had obtained some interesting results and made some interesting conclusions on that. So this is what happened when I. So this is the same thing as this one, except I put a thin converging lens pretty close to here. So I had kept the lens somewhere around here. Okay, I tried different locations, and when I put it over here, then I got this interesting concentration of light over here. Okay, so here you can see, I think, all of the colors. Violet. I don't know what is indigo, so I've never could identify this indigo. But blue, green, yellow, orange. Here is orange and red. So almost all the colors of the spectrum, except the indigo part of it. So I don't know how to. I don't know what is indigo. Can you see indigo over here? Isha is here. Where? The last part. Looks like purple to me. This region. Okay. Anyways. Okay. So, any questions anybody has about what we have seen so far? Why does Patu know about indigo? Okay, I got it. I got the answer from Isha. She's sitting here. Okay. So, anything else to discuss about this? That urge you people also to, try something out. Another interesting thing is in the pictures that you see, I had also taken a CFL bulb. So this was an incandescent bulb, and I had taken a CFL bulb also to, sorry, not a CFL bulb, what am I saying? The LED bulb, to also try it with the LED. Unfortunately, what happened was this got heated up so much, and it has been heating up and cooling down so much. When I tried to replace the bulb, the plastic parts inside broke, so I couldn't fix this bulb. But then I found another this thing. I found another torchlight with an LED bulb, with an LED this thing emitter, and I used that on this, and there was no fringe at all. There was no splitting of the light at all that took place. So I think the LED white light may be not actually consisting of the different colors, but I'm not sure how to conclude about that. So I'm still looking for some explanation to why there was nothing visible at when I used the LED bulb. Okay, so with that, I think we can stop the screen sharing and move back into things relevant to the syllabus. So with that part, actually whatever I wanted to say regarding the spectrum has come to an end. I'm just looking back at the textbook. There are a few things that are written over there that I'm sure you people will be able to figure out on its own. So the sort of the first section over here, yeah, I mean you can't really focus, but I'll just read it out to you in any case. Is that it says the deviation produced by a triangular prism. So they're talking about two deviations that happens. There are, right, in the first surface there is one deviation that takes place, and in the second surface there is a second deviation that takes place. So we talk in terms of the total deviation delta produced in a prism is the deviation produced at the first surface, signified by delta 1, and the deviation produced at the second surface, signified by delta 2. I don't think there is anything very significant about that. And they also give the three factors on which this deviation depends. Okay, and the three factors are the angle of incidence, the angle of the prism, and the refractive index of the material through which the light passes. So you can just go over those sections. There is nothing surprising about those. And then the next section reads dependence of deviation on the color or the wavelength of light. We have discussed this in much of detail, so you can go over it. There's just one thing, which is that the colors of the light and their wavelength and frequency range. Now, students have often asked me, should we memorize this chart that is there over here? So if you have the textbook, you can have a look at it. But basically, what it does is this chart gives you the the color of the light and the range of wavelength and its frequencies. Now, I would say to do something like that, to memorize the entire table, it's quite an absurd thing to do. But once in a while in the past, they have given the wavelength of a certain part of the electromagnetic spectrum and expect you to identify which part of the spectrum that is. That comes in the next unit when we are discussing about electromagnetic spectrum. But for colors, I don't know how much of it is significant. What I would suggest to you people is, you people can have a look at a book like this. Um, this is um, an old copy I picked up, Harsh Bagadia's ICSE, chapter wise, topic wise, by Arihant publishers. So what they do is they kind of break up the chapters into questions that have been asked in the prior years. So all the questions with regard to, let's say, dispersion of light and spectrum will be put in one chapter. So what you can then do is you can look through that and try to identify what kinds of questions that they are asking, for which you will need a memorized part of this table to be able to answer. So I leave that up to you. You people should do some digging through and do some research and uh, figure out what specifically you need to know about it. My memory of that is, for colors of light, they do not expect you to remember the wavelengths. Okay, but simple problems like the one that they have given over here. So actually they are using a unit for wavelength, for length in general, but wavelength in this case, a unit called angstrom. Okay, and this is a slightly antiquated unit. It's A with a sort of uh, circle on top. Reminds me of things that you'd write in Gothic or Dutch or something like that. And 1 angstrom is equal to 10 to the power of minus 10 meters. Okay, and this is kind of unwieldy because later when we went for the international system, we did not give a name for 10 to the power of minus 10, whereas we gave a name for 10 to the power of minus 9 meters. Right? We called it a nanometer. Right? And we did that because nano in Gujarati means very small. But now we had a problem because 1 angstrom we can't express in terms of 10 to the power of minus 10 because we can't use a term like this to refer to it. So therefore, we ended up saying that 10 angstroms is equal to 10 to the power of minus 9 meters or 1 nanometer. So we can say 10 angstroms is equal to 1 nanometer. So this is one conversion that you are expected to know. And the other kind of problem that I have seen asked once in a while, 2014 was the last time something like that was asked, which is that if they tell you that the wavelength of a particular radiation was so many angstroms, find out what is its frequency. So you have to use the wave equation in this case. V is equal to F times lambda. um, Velocity of all light is the same, 3 times 10 power 8 meters per second. This is in SI. And the wavelength will be given to you. So you have to manipulate that equation to get the frequency. So that is the nature of the question. There are a couple of such questions that are there in the assignment. So I will give you the assignment to take. And if you solve those problems and we discuss any issues coming out of that, then it should be possible for you to get prepared for that. So with that, we'll come to an end of today's class. Um, we have a little bit of time, so if you people have any questions to ask, you can ask. Otherwise, I will start putting the assignment on the table. Sorry, on the whiteboard. Shall I erase this part, the angstrom part? Diffraction. Diffraction actually is not part of the syllabus for class 10. So from this we move on to the electromagnetic spectrum. We'll deal with that tomorrow. And after the electromagnetic spectrum, there is this phenomenon called scattering of light. If you want us to look at diffraction, we can look at diffraction also. Okay. What is Hardik up to? Oh God. Okay. So I'm just putting the assignment out over here. I don't know how much time we have left. Hopefully there is enough. Just read out the numbers to me. Hmm. Second one. The fourth one. Fifth one. Yeah. Sixth one. Yeah. Eighth one. Yeah. Tenth one. Yeah. 11th. Yeah. 12th. Yeah. 13th. 15th. 19th. And multiple choice on. Then numerical solution. Okay, so we can make this due on Monday's class, because the next class will be tomorrow. I'll be happy if most of you are able to complete the assignment by tomorrow. Then we can start with a quick discussion. Otherwise, it's fine. Okay, so I have given the assignment. Maybe somebody can uh, take a picture or something like that, or type it out on your WhatsApp group and send it to everybody, just in case everybody is not here. Okay. Is there it? Any other questions? Any other issues? Or shall we stop here? Tanvi is asking if I'm going to give some sums on the deviation formula. I don't know if there are two numericals in the chapter for 6a. I have given both. I'm not sure those are on the deviation, but just try it out. In fact, I haven't seen any numericals based on the deviation formula so far in any board paper. I just don't remember seeing them. They might have come, but at least in the last 10 years, I don't remember seeing them. Okay. All right then. So we'll stop now and see you guys tomorrow.